Good afternoon to all of you. In the last lecture, we discuss not in the last lecture, an earlier lecture, we discuss one result related to continuous function. So this result says that if I have a continuous function f from x to y, where x and y are a topological spaces, two topological spaces, and f is continuous function that is given, and if z is some subspace of y. Subspace means it has a subspace topology coming as a subset of y. So z is a subspace topology coming as a considering as a subset of y, such that fx is a subset of z, subset of y. So what does this means is that you can consider z to be a set between these two sets, right? So z contains fx is the range of f, and y is codomain. So any subset of y which contains the range of f, you consider a function taking values in that set, then this function, what it is doing is basically we are considering f from x to z by considering the restricting the codomain to z. So that function will always be a continuous function. So for example, if I have a continuous function f from R to R, which is fx equal to sine x, then we know that the range of this function, the range of sine x is close interval 0 to 1. So therefore, what this result will give is, if I consider the same function f from R to close interval 0 1, the same function by restricting this codomain to the range or any set which contains the range, any set which contains the range, then this function will also be continuous if this is continuous function, right? So here sin x is continuous, so this restriction function which is coming as a, so this new function we can call g, and this g is defined as gx equal to fx only, right? So g is same function, only we are instead of the whole codomain R, we are considering the range. Then g is also continuous function. So that is this result. So it is continuous by considering this on Z, a subspace topology coming from Y. So proof of this result we have discussed already, but we want to use this theorem today. In connection with the connected topological spaces. So let us first revise what is the definition of disconnected topological space, which we discussed in the last lecture. So a topological space X, that means X has a topology tau X defined on that. X is any set. So that topological space X is disconnected if I can write capital X as a union of two sets U1 and U2, where U1 and U2 are non-empty disjoint open subsets of X. So if X is given, if I can find U1 and U2, which are disjoint non-trivial open subsets whose union is X, then X is disconnected. If I cannot find the pair U1 U2 which satisfies this property, then the topological space is connected. So whenever such a pair, if we can find for given X, that X is called disconnected, and this pair is called separation. the pair u1 u2 is known as the separation of X. So we will see the examples of X, different topological spaces X, where separation exists or not. So such u1 u2 exist or not. So suppose such u1 u2 exists, then we have discussed that if I consider u2 to be the complement of u1, because u1 u2 are disjoint sets and its union is X. So u2 complement is u2 is u1 complement and u1 is open. So therefore u2 is closed because u2 is a complement of open set. So it is closed. And by the property of separation, since u2 u1 u2 is a separation, u2 is open. Right? u2 is open by the condition. It is open set. So what happens is whenever we have a separation u1 u2 of a given topological space X, u1 and u2 both are open set as well as closed set, right? So it is quite confusing that how can a set will be open set as well as closed set. So we will see some examples in today lecture. And a topological space which is not disconnected is a connected space. So first example we have seen is a X with the standard topology. So we know in real analysis that if I have a standard topology on R, that means the open sets which we have in a real analysis. With respect to those open sets, any subset of the real line cannot be open as well as closed, because if the set is open, its complement is always a closed set, and that closed set cannot be an open set also, right? So that is basically the idea why R is connected space. It cannot be disconnected. And so let us start with some simple example of a disconnected space. So we will see how um, what kind of examples we will have in which the subset is closed as well as open. So usually such examples come by considering the subspace topology, right? So subspace topology is very important. So here is an example. So let R be the set of all real numbers. So this is a set and on which we have to define the topology. So we define the topology to be the standard topology. So now I want to consider a subset of R, and on which we have the standard the subspace topology coming from the standard topology. So let A be the set which is close interval 0 1 union open close interval 2 to 3, right? So close interval 0 1 union open close interval 2 to 3. So 2 is not there but 3 is there. So consider subspace topology tau A on A by considering A as a subspace of R with the standard topology. Right, so question is that is A connected topological space? with respect to this topology, subspace topology. So this is a question. So we will try to answer this question. So first of all, what is tau A? Tau A is the topology. So a set U is open in tau A or U belongs to tau A if what is the subspace topology definition? U equal to A intersection V, where V is open subset of R, and open subset of R means V is open with respect to standard topology on the real numbers. So this is the definition of topology. Now let us go further. So let us just write down what is A. So A is the set close interval 0 1 union 2 3 intersection V, where V is open in R, open subset of R. So what will be the simplest elements of tau A, so that we know that the simplest basic open sets in R are the intervals. So if I want to find the simple elements of tau A, I have to consider the basic open sets V of R, which are the intervals, open intervals, which are the basic open sets in the real line. So if I take V equal to the interval around close interval, close interval 0 1. So let us say -1 to 1.5. Then we get the open set U to be 0 1 union 2 3 intersection V. So V is, in this case, V is -1 to 1.5. And then we know that when we take this intersection of these two sets, we will get essentially 0 1. So this is open in this topology. Similarly, if we take V equal to interval around 2 3, open interval around 2 3, so then that will be, let us say, 1.5 to let us say 4. So this will contain this interval 2 3. So then set we will get is 0 1 union 2 3 intersection, sorry, this interval, which is 1.5 to 4. So whatever intersection we will get, that will be open in the subspace topology. And by the selection of this open interval, it is clear that the intersection of it is 2 3. So this is again an open setting, the subspace topology on A, right? And even we can take the interval which actually, open intervals which actually intersects with these two intervals. So for example, if we take V to be -1 to half, -1 to 1.5, then we'll get the open set to be 0 1 2 3. This is union intersection -1 to 1.5. So what we'll get is anyway, this will not intersect with this set, only this will intersect. So the intersection is 0 to 1.5. So this is also, this kind of sets are also open in subspace topology. And same way we can intersect 2 3 with this type of intervals, open intervals, and we'll get some more example of tau, right? So this way we can discuss the subspace topology, which we have already discussed. What I want to say here is note that A is basically 0 1 union 2 3, and we have already seen that these both elements are in tau A, right? So they are open. So therefore 0 1 and 2 3 are open sets. Open subsets of A in the subspace topology. And then we know that also, so let us pick some notation. So consider u1 to be 0 1 and u2 be 2 3. So u1 and u2 are both open sets, right? And then this is A is actually u1 union u2, right? It is u1 union u2. And another property what we need for the disconnected set is they are disjoint sets, right? U1 and u2 are disjoint sets. So that also holds because the intersection of u1 and u2, you can see that it is null set. So these sets u1 and u2 satisfies all the properties of the separation because they are open sets. Its union is a given topological space A, and its intersection is null set. So therefore u1 comma u2 is a separation of the topological space A. So what is topology on A? Topology on A is the subspace topology. Of course, u1 and u2 are not open with respect to the standard topology on R, right? Because u1 is closed interval, so it is not open. But when we consider the subspace topology, it is open. And now you can see that, note that u1 is closed. Why? Because u1 complement, what is u1 complement? So our topological space here is A. So u1 complement is A minus u1, and A is union of u1 and u2, from which we remove u1, then we'll get u2. Right, so u1 complement is u2, and we know that u2 is open. So since u1 complement is open, u1 is closed set, because complement of every open set is closed set. So this is an example which says that similarly u2 is also closed set. So this example we are getting, which is a, so what finally we got? We got the separation, therefore E is a disconnected topological space. So E is a disconnected because of is disconnected because of u1 u2 is a separation, right? So this is only a remark kind of thing. So this is in the bracket. That is just explanation. It is not required in the proof actually. So directly from this we will get is disconnected, because whenever we have a separation of a topological space, the topological space is always disconnected space. So using subspace topology, we can find this way the several examples of disconnected spaces, and there are some theorems also which we can use to find different examples of connected and disconnected spaces. So let us see two theorems which are very important to understand the connectedness. So first is any continuous image of a connected topological space is always connected. So we want to prove this. So essentially what we need to prove here, we need to prove here that if I have a continuous function, then its image is connected connected space. So let us consider some particular function, some general function. Let f from x to y be a continuous function, and x and y are two topological spaces. So we want to show that image of f is connected. Now if I have a topology on y, image of f is f of x, f of capital X, then f of capital image is always a subspace of codomain, right? So here what we want to show is that fx is a connected subspace of y. So that means it is connected, but with respect to what topology? So fx is connected with respect to the subspace topology on y, because fx, which is a range, is a subset of codomain y. So that as a subset, it has a topology coming from topological space y. So now we want to show this fx is connected space. So let us start with by assuming that fx is not connected, for example, then we'll get a contradiction, right? So let us start with that. So suppose I want to show fx is connected, but I will assume fx is disconnected, and then I will get a contradiction. So that way we can prove that fx is a connected space. So suppose fx is not connected, so that means it is a disconnected subspace of y. So fx is a disconnected subspace of y. So whenever we have a disconnected space, that means we have a separation u1 u2. So here also we are getting separation, therefore there exists open sets u1 and u2, open subset u1 and u2 of fx. So there exist subsets u1 and u2 which are open in the subspace topology. On fx as a subset of y. So that fx is disconnected and u1 and u2 is separation. That means fx is basically union of u1 and u2. Right? u1 and u2 are non-empty, disjoint, open subsets of f of x. So now using this information, what we will get is we can apply f inverse both the sides. So apply f inverse both the sides. We will get f inverse of fx on the left side. The same way we will get f inverse of u1 union u2 on the other side. And then we know that f inverse behaves well with respect to union. So therefore f inverse of union u1 union u2 is f inverse of u1 union f inverse of u2. Using the simple set theory, we will get that. And what is f inverse fx? F inverse fx is nothing but x. Right? So what we get is x is actually f inverse u1 union f inverse of u2. Now if we can show that f inverse u1 and f inverse u2 are disjoint open sets, then we are done. We get the separation of x, right? Because these two sets are open, then x can be written as a union of two open sets which are disjoint. So did I mention disjoint here? No. So I should mention that u1 and there exist disjoint subsets u1 and u2 of fx which are open in the subspace topology as a subset of y such that fx is union of these sets. So x is this, and note that f inverse u1 intersection f inverse u2 is f inverse of u1 intersection u2, and we know that u1 and u2 are disjoint, so this equals f inverse of null set, because u1 intersection u2 is null set, and then we know f inverse of null set is always null set. So what we got is f inverse of, so what we proved is f inverse u1 intersection f inverse u2 is null set. So therefore f inverse u1 and f inverse u2 are disjoint, and u1 and u2 are subspace of fx, right? So and f is continuous. So inverse image of open set is open if f is continuous, right? So since f from x to y is continuous, f from x to fx by restricting the range is also continuous. So this is what we discussed is this result, right? So basically z is f of x we are taking. So considering f from x to f of x, that function is continuous. what we discuss here. So since this function is continuous, what we get is inverse image of u1 and inverse image of u2 are open sets. Right? Why? Because u1, u2 are open. So f is continuous and u1, u2 are open in the subspace topology. Its inverse image is also open. And f inverse u1 and f inverse u2 are disjoint, and its union is x. Union of f inverse u1 and f inverse u2 is x. Right? So therefore, f inverse u1 and f inverse u2 forms a separation of x. So x has a separation. So therefore, x is disconnected. But our hypothesis is x is connected space. So that is a contradiction. That is a contradiction. So therefore what we get, therefore f of x is connected with respect to the subspace topology. Right? So what we proved is, basically we proved that if I have a continuous function, then its range is a connected space. So if I take sin x function, then its range is closed interval 0 1, and what this result will give is the closed interval 0 1 is a connected space with respect to the subspace topology as a subset of R, right? Because R is connected space, domain is a connected space, X is R here. So this way we can prove certain subspace of codomain, which is image of a particular continuous function, then that is also connected space by applying this result. So this is a simple result. Same way we have a second theorem. It is also related to continuous function. So if I have a function which takes values in 0 and 1, so that we can use here. So a topological space X is disconnected. So whenever I want to show given topological space is disconnected, I can prove that there exists a continuous function a continuous function f from x to the set 0 1. It is kind of binary function. Takes values in binary, continuous surjective function. So I should have a topology on close interval 0, 1, right? So on close interval 0, 1, we have a discrete topology. So we know that any finite subset of real line, by considering subspace topology, the topology on that finite set is always a discrete topology. So 0, 1 is a subspace of real line. So it is natural to consider discrete topology on that. So what is the proof of this theorem? So let us start with disconnected space, and let us try to consider to define such a function f on that. So if X is disconnected space, we have the separation u1 u2, right? So every disconnected space has a separation, and what is meaning of separation? Therefore X is equal to u1 union u2, where u1 u2 are non-empty, disjoint, open subsets. So why we are taking non-empty? Because otherwise every set X we can write as phi union X. Phi and u both are open and they are disjoint. So in that way every topological space X will be disconnected. So this we don't want. So therefore this condition is important, that u1 and u2 both should be non-empty set, right? So that's why the non-empty condition is important here in the definition of disconnected space, so that some of the topological space will be disconnected, other will be connected. So now we have a separation u1 u2. So define a function f from x to binary digit 0 1 by defining fx to be 0 if x belongs to one of the set. So let us say u1, and 1 if the other set, x belongs to the other set. So if I define f in this way, first thing I want to show is f is a continuous function. So to show f is a continuous function, what I want to show? I want to show that inverse image of every open set is open, right? If I can show that, then f will be continuous. So the open subset of 0 1 in the discrete topology are nothing but null set capital X, singleton 0 and singleton 1. So let us find the inverse image of all these sets. So f inverse 0 is u1, which is open. F inverse 1 is u2, which is open. F inverse null set is null set, which is also open. And F inverse of 0 1 is the full set, which is also open. So therefore inverse image of every open set is open. So f is a continuous function. Just f is a continuous function, and also f is onto function. Why f is onto? Because if you take x belongs to u1, then fx is 0, and if x belongs to u2, then fx is 1. So both values 0 and 1 of the codomain is attained by f. So f is continuous function which is surjective. So it satisfies the conditions of the hypothesis, right? That is what we want. We want a continuous function f uh, which is onto and it takes values in 0 and 1. So one part we have proved that if I have a disconnected space, I can construct such a function which takes values in 0 and 1. Now conversely, we want to show that if I have a continuous function which takes values in 0 and 1, then we want to show that f is a disconnected space. So conversely, suppose that we have a continuous function f from x to 0 1 which is onto, right? I have a function which takes values in 0 and 1 which is continuous, defined on x, and it is onto function. So what I want to show is I want to show x is a disconnected space. So let us assume that x is a connected space and then we will find a contradiction, right? Same way we will do. So assume that x is a connected topological space. So now x is a connected topological space and f is a continuous function. So the theorem which we proved, the previous theorem, what that says, if I have a continuous function defined on a connected space, then its image is a connected space. So what we get here is we will get the image is connected, and what is image of this function f, because it is onto function. So image is same as the codomain, and codomain is 0 comma 1. So therefore by previous theorem, f of x is connected, right? So therefore what is f of x? F of x is basically 0 comma 1 is connected in the, what is the topology given here? Discrete topology. Now question is that whether 0 comma 1 is connected in the discrete topology or not. So in the discrete topology we know that every subset is open of the given set. So note that I can write 0 comma 1 as a union of singleton 0 and singleton 1. So basically I am taking u1 to be singleton 0, u2 to be singleton 1, and we know that u1 and u2 is are non-empty, disjoint because singleton 0 intersection singleton 1 is null set, and it is open subsets of 0 1 in the discrete topology. Right. So what we proved is that singleton 0 1 is basically disconnected. So therefore 0 comma 1 is disconnected in the discrete topology. right? So what we are getting is on using that theorem we are getting 0 1 is is connected space, but actually 0 1 is a disconnected space, right? So therefore we get a contradiction. So what is correct is that 0 comma 1 is a disconnected space, but by applying that theorem we are getting 0 comma 1 is a connected space. So that is a contradiction because 0 1 is disconnected space. So that is happening because what we assumed is wrong. We assume that X is a connected space, therefore X is a disconnected space. So essentially we proved that if X is disconnected topological space if and only if there exists a continuous function which is onto and it is defined from f to x to 0 comma 1. So these are the main result which I wanted to discuss in this lecture. If you have any doubts, you can ask.